Could never return from this awful place. Of course I'm funny, and you should be too. Landed Calrissian and poor Chewbacca could never return from this awful place. Of course I'm funny, and you should be too. Landed Calrissian and poor Chewbacca could never return from this awful place. Honored by your presence. You made it. You may dispense with the pleasantries, Commander. So, Commander, for your sake. You may dispense with the pleasantries, Commander. I hope so, Commander, for your sake. Honored by your presence. You may dispense with the pleasantries, Commander. Christian and poor Chewbacca never return from the...
Oh my god. Stuart! Stuart! It's live, man! They're here! Oh my god, what am I going to do? Oh man! Right, okay. Breathe, I can do this. I can do this, it's okay, right. Hello, world! I am really the guinea pig, and Stuart is running a little bit late tonight, so it looks like I'm doing the intro this evening. Wow, okay. So, tonight on the show we have Ben Trolley, who is a very, very clever person who knows lots about numbers and science and space, and he likes music, and it's all very good. So he's got to be on talking to Stuart in not too long. I know if Stuart was here right now, he would probably want to thank everybody for joining and watching the show. He's a very happy person at the moment, and you know, it's nice to be able to talk to people at the moment whilst locked up at home with the coronavirus and all that. So thank you for sharing, and thanks for watching, everybody. And I'm going to keep doing this for as long as possible. Right, Stuart! Stuart! Where are you now? Come on, you've got to do this show, man! You can't just leave us here doing this myself, like. This is fucking brutal, pal. Alright, okay, right. You've given me some food though, that's quite nice. Let's get into this food. Yes, pal. I'm getting that food. Yes, I am. Right. Stuart, right. I'm done. I'm gonna eat this food now. I'm gonna run the first bit, so enjoy the show, everybody.
Hello. There we go. Right. Let's get Ben on. Da-da-da. Here we are. Ben, how are we doing?
I'm good, thanks. How are you, man?
I'm very well. There we are. Sorry about that. Yes, I'm very good, Ben. I'm very good. How are you?
Excellent. I'm all good. A little bit nervous. It's been 4 years since I really did any of this
Oh,
stuff.
don't be nervous.
Aside from just talking people's ears off when I'm a bit pissed. See how it goes.
Yeah, well, we've definitely had some awesome conversations over the last few years talking about some sci-fi novels and talking about different bits of maths and science. So I'm sure everyone is going to really enjoy it, man.
Fingers crossed.
Can I ask you? I can hear a little bit of echo through my earphones. Would you be able to turn me down a little bit on your end? So make sure you can still hear me. If not, I can sort of make do.
I think that should be fine. Pretty sure I can still hear you. Is that better?
Okay, cool. Yeah, that's fine. That's going to work for me, man. That's awesome. So really, well, how have you been since the world changed and all that? I guess a quick catch up before we jump into the deep space shit.
I mean, I feel like I'm one of the lucky few. I'm in a situation where essentially, because I was already on universal credit before this whole thing started, I'm still on universal credit.
Yeah.
So I've got enough money to like not be homeless and to have food and that. So currently I'm just kind of working on my solo stuff, trying to scrabble together some form of something that I might be able to use to make some money out of music
Sure.
before we can perform again.
Yeah. Well, everyone's getting pretty inventive, that's for sure.
Yeah, absolutely. I mean, I've been doing a lot of writing and a lot of like practicing of stuff that I haven't had time to practice for ages, between doing a physics degree and then going into like doing wedding bands and having a lot of stuff to do.
Yeah.
So yeah, it's basically just been working on whatever I would be working on if I had no exterior like forces making me do other things.
Definitely. I think that's been one of the nicest silver linings from the whole thing is that, well, one thing, as I mentioned to Stan, our first guest when he was on, was like he's managed to see his family loads, and I think people have managed to take the time and realize, wow, we've got all like never had this time before to really bond and all that. And the other thing is, it's like that list of things that you never really were going to do. You can't avoid it anymore. You're like, okay, right, I need to tick some of these off now. And you can see everyone's going through their list and doing what like things that are really close to their passion and things, which is nice. So I've you obviously playing lots of bands and stuff as well. We played together, and I think had you been planning to play with Pygmy Twilight? That's like the Frank Zappa.
Yeah, we've missed the tour we were going to do, but that's been pretty much all rescheduled. We were just going to do like a little weekend thing, going down south for a 3-day little weekend kind of deal.
Okay. What's happening there? Yeah. Where are you playing down south?
We were playing a gig with the Treacherous Cretins in London.
Yeah.
Which I can't remember which ones have actually been. I think we've definitely got a tour rescheduled for next year.
It's a long way away, so don't worry if you don't know the dates.
Yeah, I mean, I put it all in my calendar and then forgot about it pretty much.
Yeah.
And I think there was some weirdness, like one of them has been rescheduled for a slightly different time for some reason. I'm not sure why that is.
And so is that well into next year, like once things have likely opened up again? Or
I think it's February.
Cool.
The ones that have been rescheduled, because I remind it was a few months earlier than what it was supposed to be this year, which was May, maybe.
Wow.
Time's kind of lost all meaning.
It is that like it's all coming into one thing for me as well. Like waking up, I was like, I'm glad I've got this to focus on now. It's really taking my focus and giving me things to do every day and like giving me a bit of structure, which is nice. I'm going to just throw up. I was having a nightmare the other day on the News of the Void news from the Void show, which is sort of more interactive, and I was struggling to get comments and things through. So we're actually getting comments and things now. I just want to check it's all working. So we'll just see what people are saying. Let's see if we can get this to. Here we go. Hey, it's working! Yay! Great. So for the next news of the Void show, I'll be able to talk to you properly and interact properly, everyone. That's Alex Weir. Alex Weir's actually coming on this Thursday night to do a deep dive. We're going to talk just generals, life, the universe, and everything. What else have we got? Don't know. Lisa Shaw. Hi, Ben. Tessa. Hi.
Oh yeah.
Yes, I'm glad this is working. Great to see everyone watching. Hello.
Hey
Sam
Sam.
Barnes. Geez, someone's been in lockdown too long. Yes, absolutely. Thank God I have
We
a guinea
all.
pig. There's my mom. Hiya, mom. How we doing? Hope your eyes feeling better. Okay, I'm Matthew Riddle. Hello, Matthew will be coming on. We're going to be doing a music side to this whole show as well, so I'm sure we'll get you back on for that as well, Ben, once that kicks off. But we're going to teaming up with sound, and Math's actually going to come on do some tunes for us and things when that kicks off next week. But right, okay, so we're here to talk space, and like I've got a few questions, not too many, but I'd like to ask you. But I guess we'll start off with like you studied physics. Where did you study about?
I did indeed. University of Edinburgh. That's why I'm in Edinburgh now. It was actually originally I went to Edinburgh because it was one of I think 3 places in the country in the UK that had a physics and music combined degree, and that was what I signed up for originally. I think the other 2 were Royal Holloway and Cardiff. So I went to open days as a and Edinburgh was just better. I could tell straight away. And then I just loved the place so much that I stayed.
Yeah, that happens a lot.
Say again?
That happens a lot. People come to study and they end up living there the rest of their life. The rest of their life. Which is it's a common story. So you did was it 4-year degree?
A 5-year degree, because I did the extra year that I didn't technically need to do coming from A levels, but I'd had a gap year, and
nice.
It was definitely a good spot.
What did you do in your gap year then?
My gap year, I mainly taught and got really high.
Where did you taught?
Yes, taught music. I was teaching at a music school in Scarborough.
Cool. And so it's
I was teaching bass and keyboard and music theory.
A nice break from like hardcore physics.
I mean, at the time, I hadn't really gotten that hardcore into physics. Like, I'd only done physics at college alongside music and maths and philosophy and whatever else.
Okay, all right. So this was before you actually went to uni. I thought you'd
So I had my gap here, and then I came up north and started the whole thing.
Well, I think that's a good way to do it, is you get to see a bit of the world, and then I kind of went straight from high school to college and was a bit mystified by the process of just going straight in, and I think I could have benefited from just having a year to be like, oh look, this is kind of how the world works out with like a education facility.
It was really just good to have. That said, I didn't really get to see much of how the world works outside of an education facility since I was still working in an education facility. But no, it was mainly just to take a break. I'd worked pretty hard in A levels once I realized that I needed to, kind of halfway through my first year of college. And then I was like, right, take a breath, because this is going to be another 5 years of even more of that. So it was a good call. It was very good for me. And it meant that when I got back to uni in Scotland, where they've got that kind of not quite A level, not quite university level year, that was a really nice intro, like getting back into stuff, and it just worked really well.
And so
that was very nice.
Once you got to uni, then like obviously you done well at physics in high school and stuff. Like, was there anything particular out with like your experience at school that made you want to go do physics? So, like just your general interest in it, or did you find that you had a really good teacher that got you into it? You know, sometimes it's a really good teacher, you know.
I mean, shout out to Colin Fallows and Mr. Brinded from Lady Lumley's when I was in secondary school.
Big up him. There's always a
Big
teacher
up
in the
those
background.
Two at least, and my parents. I mean, like, I kind of feel like that kind of interest in the world that I see is why I did physics. I think I've kind of always had that, and it's always been really encouraged. Like, one of my earliest memories was being in the car with my mum and my big sibling, and they were in the front because I was can't have been more than like 5 or 6 at this time. So my big sibling was 9 or 10, and they were talking about the ingredients of the universe. And I just remember them talking about these quarks and protons and electrons and things, and how they all fit together to make us and everything else, and just being absolutely fascinated by the whole thing. And I guess that's just kind of carried on ever since, really.
It is such a fascinating thing. I know I'm like I'm like myself. I haven't studied it or anything, but I very actively follow all science journals, and I read up and watch all the things I can. And for me, it initially started as a fear. I think I remember being worried that the world was going to get hit by an asteroid, and I think out of that fear, I remember watching this Sam Neill space program on the BBC when I was really little, and it was like dinosaurs coming in. It was quite sort of American scaremongery, like it could happen tomorrow, like beware. And like I was like, oh no. But I think out of that fear was like, space, how does that work? And the more you figure out about it, the less scary it becomes. And it then became extremely fascinating to me, especially once I got into bands and started smoking weed and stuff, and you sort of let your mind go to those places. It's a beautiful place to ruminate. So you're at your university and stuff. What really stood out to you on that course? Like, let's get into it a bit. Like, what were the things, like, if you were trying to convince someone in a bar of one of the coolest things about physics that you like, what would you say?
I mean, I feel like they're kind of different questions, because I don't know if what I like is necessarily representative. But the things that have always fascinated me the most are essentially the most basic things. I just want to know, at the most basic level, how do things work? So that always boils down to, what are the fundamental smallest bits, and how are they fitting together, and how are they interacting to make everything else? And like, obviously there's flaws in that statement in terms of practice. You can't use a Schrodinger equation to simulate biology. It's just impractical.
And
even with the most powerful computer in the universe. Yeah, there's just no point. You might as well use statistics, as much as I hate to say it. But yeah, so the most fundamental way things work, the mechanics, the particle physics, the quantum stuff. I really love quantum stuff, because I also love things that blow my mind.
And it's just in the territory, isn't it? It's like,
yeah, it absolutely is.
The fact that quantum physics is a tangible thing that we know an awful lot about now, but then like the sort of the implications of that to the real world that we sort of exist in, and we've got physical properties like this. But it's when you start thinking about quantum physics quite deeply, and you're like, that's when I start getting kind of weirded out, and I'm like, oh, is this just like,
I mean,
is this one of the multi-worlds or like a simulation?
You've always got a safety net of the correspondence theory. I mean, maybe the simulation question's a bit different, but correspondence means that the things that we see are still valid. Like this mouse resting on my knee, that's still a thing. Just because you can say that you can talk about the electrons and on this incredibly tiny scale, that these things aren't even touching, and there's a huge void between the atoms, etc., etc.
Yeah.
That doesn't change the fact that this mouse is resting on my knee. See what I mean? So all of the quantum stuff has to scale up and become Newtonian physics. And that is fundamentally baked into all of quantum physics.
Right. But isn't there is problems in the, like, how they meet up though, right? And that's where the sort of the debates are happening between, like, we can't, because maybe I'm going too deep in here, but like because of the way quantum physics works, a lot of the experiments do leave like ambiguous results, which like are hard.
Not really. So
okay, yeah, tell me about that then.
It's more that the results are statistical, and that because the theories being statistical and being to do with probabilities means that you can't say that you've got a result from just one interaction, because that interaction will happen differently every time due to just whatever physical laws are at play, being fundamentally probability based. So you get distributions, you get a range of results happening, and they'll usually form some kind of bell curve if you plot the right things against the right other things. And what we're looking for is corroboration between the bell curve that we see from an experiment and the bell curve that we predict from our theory. And if they match up, then we say that our theory is good. So, for example, quantum electrodynamics predicts the value of a particular fundamental constant called the fine structure constant. And it predicts this very, very precise number because it's based on other very precise numbers. And we've also measured that in an independent experiment. And they agree to 15 decimal places, which is just absurd. It's mind-blowingly accurate. So actually one of the most accurate results in science is a quantum result.
Whoa, okay. And so what are the implications of that being so corresponding so much onto that level, like 15
it's a really big problem when we get to things like relativity and we can't make gravity and quantum physics work, because relativity is also similarly well tested and similarly accurately known where it applies.
It seems like it's on a good footing, that idea.
Yeah, so we have these two theories that are incredibly well, corroborate incredibly well with all of the physical evidence that we've managed to gather that corresponds to each of them. And yet we can't make them play together nicely, which is the biggest problem in kind of physics and stuff, as far as I'm aware. Still, do you think the unification problem?
That's it. I've watched a lot read a lot about this that's what I was trying to get at before, but my words were failing me. Is like unifying these ideas and knowing that X is correct and knowing that Y is correct, but then having this problem occasionally where like what you were describing with it's
essentially most things are either one or the other. You're either at normal Newtonian scales like we are and things work as we expect them to, or you're going super fast, or you're in an incredibly deep gravity well and things are really big, or it's really tiny and you're on a quantum scale, and you don't get that much overlap until you get to things like black holes and neutron stars, and then it gets a bit different.
Yeah. So I think
that's why they're the most interesting bits.
Yeah. And the thought experiments that come alongside them tend to be the most thought-provoking and like cerebral, where like, I mean, that's where I that's where I kind of get drawn in, is like these ideas and how they might play out, or the possibilities of what they actually mean. Like, I mean, what's your thoughts on things like multi-worlds theory or the multiverse, and how that might fit into things like quantum physics? Is that totally crazy, or is that?
It's a valid mathematical interpretation, as far as I understand. Cool random link. You know the band The Eels?
Yeah, I love them.
Yeah. His dad, Mark Everett II, I think he's Mark Everett III.
Yeah.
Well, either way, names don't matter. His dad was the guy that published the original many worlds quantum interpretation as a valid scientific paper.
He was a crazy guy. I've heard about, like, I've been given a book from the guy that's in the Eels, and apparently it's mostly about his dad.
Probably, yeah. There's a lot of chat about it on the documentary thing that I watched, which is really interesting. I think it was on the BBC at some point years ago.
Cool. I'll try and find that and watch it.
Yeah, it was really cool. It was very interesting. His dad was the guy that first published that theory, and it's as far as I'm aware, I haven't ever looked into it specifically. I've never read the paper or anything. I feel like it'd probably be a bit above my level. But as I understand it from people who have, it's a valid mathematical interpretation of the ideas of quantum theory. Because one of the problems with the things that quantum theory tells us is that it is so contradictory to our everyday experience. So we have difficulty getting our heads around it. So we have these interpretations. So for a long time, the Copenhagen interpretation was the dominant one, which was essentially the one that you'll see of the probability function of quantum mechanics being. I'm forgetting the specifics of the different models because.
No, you're okay. I mean, just generally, I mean, I get what I can see what you're getting at. And it's maybe this is a good time to bring up the double-slit experiment then.
Yeah, I mean, this is one of the experiments that I think it was just before the Copenhagen conference, the Solvay conference, where all of the greatest scientific minds of the day met and decided on these things. And the Copenhagen interpretation was the one that came out of that, which was, I think it is just to do with it being a probability function, and you're saying that there is a certain possibility of the particle appearing or being at any one of these points as and when it's measured. Yeah. It's that idea of it's a wave until it collapses, and the wave function collapses tied into the Copenhagen interpretation. But it's not the only interpretation, and that's the important bit that loops back to what we were saying about many worlds.
Sure. I feel like the double-slit experiment. Sorry, I'm talking over you. Keep going. That's all right. I was going to say, I was basically just finishing up that's the many worlds interpretation is just another way of looking at it, where you're saying instead of in our universe the wave function collapses, you're saying that the particle is in every single place that it could possibly be, just each one is in a different branching incarnation of existence. Wow. A different branching incarnation of existence. Yes. So every time more than one thing could happen, both those things happen, and it just splits off. Well, I believe there's an app that actually splits the wave function, and there's an actual machine in Switzerland. It's nothing to do with the LHC or anything, but the app is connected to this machine in Switzerland, and when you hit this button, it actually splits. It performs some task which splits the wave function, and that's this guy that was talking about multi-worlds on Joe Rogan at some point mentioned it. And as a way, I think it's more of a way of for folk to conceive of the idea of multi-worlds, and it's more of a tool for teaching than it is, I don't know, actually splitting the universe. And well, who knows? He seems to believe it. From extrapolation, I'm guessing what the idea of that is that if the many worlds interpretation is correct, then every time you press that button, you're creating two universes. It's kind of skipping past the point that every time you have a thought, you're creating infinite universes. But hey ho. So that's the kind of thing I think you've got to think quite that's the kind of realization that takes a while to come to. You've got to think quite a lot about what it actually means that every time more than one thing could happen, both those things happen. If we get around to talking about types of infinities, I think that's one of the biggest types of infinity, the number of universes that could exist, but it might also be a countable one. I'm not sure. That's getting... You're blowing my mind, man. How can there be how can one infinity be smaller than another infinity? How? There's not really a short, I can't give you a short answer. I don't think. So either we digress onto that or we come back to that in a bit. Are you there? Sorry, I'm here. Yeah, this is how it's going to work, I think. It was let's just go where the conversation flows. So okay. Are you ready to do it? Let's do types of infinity. I've got my head is open and ready for all right, cool. So for to be blown. Let's start off with a few just bits of words because they're important. So we need to know what the natural numbers are.
which is just counting numbers 1, 2, 3, 4, 5, 6, 7, the positive integers if you want to be mathematical about it. And for the time being, we'll think about them, and then we'll think about the real numbers. And the real numbers is all of the numbers that you can write down, essentially. So 0 point anything.
Got you. Yeah.
And then 1 point anything.
I'm with you so far.
So the whole idea of the decimal system is that you can extend it arbitrarily far. You can make changes to a number arbitrarily small. So you can have 1 point an infinite number of things.
Okay.
If it's 1.8 recurring, for example, you just 1 and infinity 8. That is a meaningful concept.
Yeah, I can follow that as much. Yeah.
Yeah. So the counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. They go on to infinity, right? They carry on.
I trust you. Yeah.
I mean, we don't know of any time that you would have to stop counting. If you had infinite time, you could count infinitely far. And our ways of talking about numbers are constructed to do that. So
you know, I did on a side note, I did do this calculation once with a friend of mine, and I believe it would take to count to 1 million would take about 13.2 days. If you were doing a second, if each moment was a second, how many moments would it take to count to 1 million? Anyway, as an aside, but what you're saying is like it's
good maths to do. If you want to try and think about things like how big a billion is, do that same calculation for a billion after you've done it for 1 million, and you get some ridiculously big number, like it's 10 months or some shit. Like, yeah, it's crazy.
Right. So yeah. So real numbers, as much as you can actually, if you were to write
natural numbers, counting numbers, they go on until infinity. There are infinity counting numbers. You can count from 1 and you don't have to stop.
Got you.
So then, as I was saying about the real numbers, we've then divided the distance between 0 and 1 into infinitely small chunks.
Right. So that smaller section is now being split into. It's like zooming in, and seeing all the
you don't have to stop zooming. You don't have to stop zooming either. You can zoom in as far as you want to infinity, and our number system allows that. The real numbers allows that.
Okay.
So we've got this little slice of an infinite number of things that has an infinity within it. So
I understand. Yay.
Clearly, the number of real numbers, which is infinite, is bigger than the number of natural numbers, which is also infinite.
You're right. Yeah.
So the guy that kind of first realized this was this guy called Georg Cantor. I don't know if I've pronounced his first name right. I think that's correct. Either way, he was a real smart dude, and he invented something called set theory or group theory, which it turns out is like absolutely foundational. It's super important for a lot of particle physics, and it's basically the best way we've got of kind of analyzing and assessing whether things are valid. We use it to build theories, like to understand why 1 + 1 equals 2. So it's like the most foundational maths you can get. But for a long time, people just thought that it was trivial, that, yeah, you've got a set of numbers, that's fine. What's your point? And it was Cantor that started realizing that things like the number of members of a set and correspondences between sets were important things. So he started thinking about this, and he realized that if something has a one-to-one, if a set, all the members of a set can be counted, they have a one-to-one correspondence with the counting numbers. So the infinity of the counting numbers is called a countable infinity, because you can count to it if you had infinite time.
Yep. I need a lot of time.
You would need a lot of time, infinite time.
Oh God. Yeah.
Whereas the infinity of the real numbers is called an uncountable infinity, because just to get from one point to the next, there's an infinity of possibilities in between them. So you can't count all the real numbers. You can't write every single one of them down, even if you had infinite time.
because you got an infinite amount of spaces in between each of those numbers, almost fractally going in on itself.
Yes, fractals are a good way to think about it because it's that kind of self-referential, repeating over different scales kind of thing.
As it gets bigger, it gets smaller, and you just keep zooming into the same iteration.
Yeah.
Oh, that's it.
Yeah. So you get your set theory stuff where he's thinking about countable and uncountable sets. And he realizes this thing that you've got different sizes of infinity because these sets have to be different. And that's about as far as my knowledge goes. But there are a whole range of wonderful videos on YouTube that I highly recommend watching. There's several by a fantastic YouTuber called By Heart, who unfortunately doesn't do much anymore.
Yeah.
If you just search By Heart Infinity, you'll get like 4 or 5 videos coming up straight away, all of which are amazing. Numberphile do a bunch of good ones. Basically, any maths or science YouTube will have some interesting offerings on these subjects. And they will probably all do a much better job of explaining them than I have.
Dude, you just made me understand types of infinity in like 10 minutes, which is quite mind-blowing. So thank you. I actually grasped the idea. You explained it well.
I mean,
what we'll do is
like an hour or so before we started reading up on that, because I was like, if I'm going to talk about this, I need to remind myself how it goes.
But what we'll do is with these shows, we're going to stick all the links and everything anyone mentions like on the Facebook page, on the event page, and in the YouTube comments and stuff. So things we do mention, I'll get a list of you after we finish, Ben, and folk can find the things that. Okay, so types of infinity. I've got some slides and stuff here which I'd like to share. So we can maybe just use them as a means of what to talk about next. So I'll just bring them up and we'll see what's there. We've got some cool photos and things. Here we go. And just while I do that, we've had some more comments coming in. So here we go. Sam Barnes again. That intro was far out. Is this Advanced Space Socialism? Hello, Advanced Space Socialism.
Oh wow! Hey,
this is excellent. Well, thank you. The Disney Family Adventures. That's my cousin's. If you want to see cool videos of Disneyland and their travels on holiday, it's a really good channel. Documentary was good. Tessatron. There we go. And I think this one's for you personally. Pringles hand. Oh no, I see what's happening here. Right, I think
that's Tess and her mum having a wee conversation there.
It's nice. That's good. This is it's a community we're growing, so talk away in the comments. It's nice to see it. Right, I think I've done it. I'm still learning this little thing. Right, can you see that?
I can, yes.
That's a black hole.
Very small. I have to lean far in.
All right. So I'll try. Well, what I'll do is I'll explain exactly what's there. And we can.
I'll tell you what. If I've got my big screen up as well, so I can look things up if I need to. So I'm going to find you.
Ah, okay, yeah. Let's use technology to our benefit. Right, I'll give you a second to get that up, and I'll talk about this. I seen this the other day. If you're not on, if anyone's on Reddit, like I follow loads of weird subreddits and things. It's a good way to find news, and generally, the comments is where the actual news is. Once people rip the headline to shreds or be like that's fake news or whatever. But they've got a great subreddit called Our Conspiracy, and I seen this the other day. It was fun. What else have we got? So on the news channel, we do headlines and stuff. We've got some cool things lined up for that later in the week as well. We'll get more folk on to talk about some of our basically just what's happening in the world. There's an awful lot going on, so I'm going to try and direct the things specifically towards certain subjects, because that first episode was a bit crazy and a bit haphazard, which was fun. It had to be done that way. But yeah, a bit more focused chats. How are we getting on, Ben?
I'm good. I've got it up on the computer. It's maybe like 10-15 seconds behind.
That's fine.
What I can see on my phone, on Tessa's phone, because my phone selfie camera does not work. So I can see you've just switched up to some fancy pictures. Oh yeah, I can see them better now on here as well.
Perfect. That's
it. Are we going platonic direction?
Go. Can we? Because I'm obsessed with these. Like, I've been like into Randall Carlson stuff, and I watched his like 2-hour sacred geometry talk, and like I just love Egypt and the pyramids and the Mayans and the fact they knew all this stuff so long ago, and I feel like we're like the dumb ancestors of these like really smart ancients, and that's why I love these shapes.
I mean, there's some things that we have no evidence that ancient societies knew of, like where I want to go to some higher dimensional shapes. I don't think there's much evidence of higher dimensional shapes being understood by ancient civilizations, but I could be wrong. But I think the kind of number systems that we use today, I believe, also are relatively modern inventions, and without those kind of number systems, it's quite hard to develop these kind of thoughts. Like back in the day, people like Al-Khwarizmi fucking writing out equations in full sentences, like a paragraph instead of a short line of algebra. And that's why they invented algebra just after that, because they were like, this is impractical. We need a better way of doing this.
Okay.
So I believe things like algebra didn't exist in the ancient world. Maybe people will correct me if I am speaking out my arse here. I apologize.
I don't know. Like I mean, to me, something like, regardless of whether they taught it in their classes or not, like when you look at their architecture, it's obvious that they knew, like.
Oh, don't get me wrong. I'm not belittling.
But more geometry, like I'm talking about, like more geometry, like trigonometry, things like that. Even like those things and the correlations between that and the likes of the old calendar and like the furlong, the mile, and I find all those like things very interesting too. How they sort of coalesce.
Mm-hmm. I mean, it's fascinating. There's certainly a rich history of like really clever people doing an awful lot of very good stuff.
Yeah.
And as you say, sacred geometry, things like music.
Yeah, like that whole aspect too. Like it's all there as well. It's like what?
Indeed. But yeah, I've got a thing that I'd like to just kind of mention before we get into the subject of the platonic solids and stuff. There's a sequence, and it goes 1 1 infinity 5 6 3 3 3 3 3 3 3 3 3 forever. It's a fascinating sequence. Do you have any guesses what it might be? I would be surprised if you did. It's ridiculous.
Say the sequence again.
1 1 infinity 5 6 3 3 3 3 3 3 3 3 3 3 3.
Is it God's telephone number?
I like it. It might be actually. It's the number of regular polytopes in the amount of dimensions starting at 0. So a regular polytope is essentially a platonic solid, or rather a platonic solid is the 3D example of a regular polytope. It's a shape like a square or an equilateral triangle where all of the parts of it are the same thing, essentially.
All of the parts of it are the same thing. So it's like what you're saying first, like the simplest version of that.
Well, and not necessarily, because like you've got squares and triangles and pentagons and hexagons, yeah. all kinds. That's the infinite one, because you can make a closed shape in 2 dimensions with any number of sides of the same length.
Okay.
In 1D, there's just a line. That's all you can do. And in 0 dimensions, it's just a point. That's all it is. So that's 1, 1. Infinity for 2 dimensions, because you can have any number of sides on a regular shape. And then when you get to 3D, something quite interesting happens. I should have drawn some things. I'm not going to try and draw live. Essentially, the idea is that with the same regular shape, so those regular polygons from 2-dimensional, we can make 3D shapes. So if you think about putting 2 equilateral triangles together on a side, if you fold them into a 3rd dimension,
then you're starting to make.
You can't make anything with just 2 of them, but if you add in a 3rd one, you can make your pyramid, your tetrahedron. It's not a tetrahedron. Can you? I'm second guessing myself. Either way, it's easier to think about with squares. So if you put 3 squares together on a side, and then you fold them up, they make a corner. And then you can do another one, slot them together, and you get a cube.
Yep, got you.
That's one of the platonic solids. The other processes are very similar. The interesting part is when you get up to 5 and 6. So it turns out the biggest number of sides that you can make a 3D shape with in this way that will form a 3-dimensional regular polyhedron or a platonic solid is 5. So you can make the dodecahedron, I think it is, out of pentagons by doing that same thing. You put a bunch of them on a common side, you make a corner out of it, and then you make a couple more of them and slot them together, and you've got a dodecahedron.
That's my favourite, the dodecahedron. What's your favourite?
Of the platonic solids?
You've got to have a favourite.
I think I like the octahedron.
Ooh, yes, octahedron.
It's
a popular one. Anything with oct is quite nice though too, because it's just a nice, like, octopus.
It's such a pleasing shape, and also it's kind of also cubes because it's the dual of a cube, and we'll come back to that later.
Do you see that graphic I put up just now with the lots of different shapes? I felt that's kind of what you're on about as we start to build up the shapes from a line, a point,
and I think
a
we've
line.
got some maps of higher dimensional things going on there as well, possibly. Fancy shapes.
It does get, like, I mean, the original platonic solids are there, but it starts to go a bit crazy towards the end of that with more of them. I do have some more here.
So just to finish off what I was saying, if you get up to your 6-sided shape, your hexagon, you try and put them together so that they make a thing. You just make a flat space. You make a hexagonal tile, which we've all seen plenty of times. So you can't make any more platonic solids beyond pentagons and the things that we've made with things with fewer sides than pentagons, which is cubes.
There is a
dodecahedrons.
physical limit to what you can actually achieve with this. Is basically there is an end point. There is no infinity to this. Platonics are
except in 2 dimensions, because you've got infinity until you get to a circle. But once you get above 2 dimensions, you've no longer got infinities. So 3 dimensions turns out, 4 dimensions, going up another dimension, turns out that there are 6 of the regular polytopes in 4 dimensions, is how mathematicians talk about it. Once you get above 3, they don't have special names anymore because dimensions above 3 aren't special, apparently. I think that's
dimensions
around naming them.
I think
so,
let's do dimensions. Like, I can just about cope with 3 today, I think. As we keep going, right, okay. So let me get this back up. So keep going, Ben. Sorry.
Cool. So so if we do that same process where we stick a bunch of 3D platonic solids together on a side, like, for example, imagine sticking 3 cubes together so that they're all sharing a common side, like we did with the squares before.
Yeah.
And then, like we did with the squares, we folded them out of 2 dimensions into a 3rd dimension to make a corner. And this is where it gets tricky. We fold our 3 cubes out of 3 dimensions into 4 dimensions to make another corner. And then we can do that a couple more times, and we end up with a 4-dimensional solid that's made up of 8 cubes.
Whoa.
In the same way that our 3-dimensional cube is made up of 6 squares. Each of those squares makes up one of the outside faces of our cube. What each of those 8 cubes then makes up one of the outside cubes of the hypercube, the tesseract, whatever you want to call it.
And so, like, there is this relationship then between dimensions, similar, like, again, kind of like a fractal relationship where, like, as above, so below, it'll keep.
Well, kind of, because that's where you get this weird sequence. So you remember it went infinity, 5, 6, 3, 3, 3, 3, 3, 3.
Right, so that's
then,
that number you mentioned is that relationship I'm trying to mention.
Yeah, so once you get above 4 dimensions, it turns out that because of the way this whole construction works, and the way lines work, essentially, that you can't really make any more regular polyhedrons after a certain point, but you can continue making hypercubes in higher dimensions by using that same strategy of stacking 3, making a corner, and sticking a bunch of them together. And you can do a similar kind of process with simplexes, which is triangles being extrapolated into higher dimensions. So that was how we get the tetrahedron. And then the 5 cell is the simplest of the 4-dimensional regular polytopes, which is basically you make a tetrahedron and then you kind of just add another triangle in a new dimension, and you can do that arbitrarily many times to get crazy higher dimensional simplexes. And you can also do a dual operation, which is where you swap the corners and the faces. So if you imagine having a cube and you take all of the faces and replace them with corners in the middle of each face, and you replace all the corners with faces connecting those corners you've made. Probably not a great thing to try and illustrate with my hands, but anyway, you get an icosahedron.
You're doing a good job, man, don't worry.
It's if you see some illustrations, if you look it up after this, there's tons of illustrations about. But yeah, essentially, it's kind of like if you switch the sides of a square with the corners, you just get a different square. It's that same kind of idea, but in 3 dimensions and above it gets a bit more complicated. So the icosahedron is the dual of the cube. You get 4-dimensional polytope, the 16 cell, which doesn't have a special name, and that's the dual of the hypercube, and you can carry on doing that into as many dimensions as you want. And like with a triangle or a tetrahedron, if you take the dual of either of them, it just becomes the same thing again. So the simplex series, the ones that are triangles being extrapolated into high dimensions, they are their own duals. So you've got these 3 things that carry on. You've got your cubes, your simplexes, and your duals of your cubes, and they can all extrapolate into arbitrarily high dimensions, and nothing else can, because of that same process of once you get to 6 sides in 2 dimensions, you get a tiling that fills space, and if you have a septagon, you can't make a corner from them. You don't get enough.
So just you reach the dead end eventually.
Yeah, you need to, if you want to make a 3-dimensional shape out of septagons, you need to add in some real thin rhombi to fill up the gaps.
You need to go down B&Q, get a bit of wood, and like edit it and cut it to squeeze it in.
The important part there is that it's no longer a regular polytope. It's no longer the same idea as the platonic solids and the regular polygons.
So those are the things. So there are platonics which people have edited once they've reached that dead end with this extra thing.
Yeah, essentially.
Wow.
So you realize that you can't make any more platonic solids in 3 dimensions, and then once you get above 3 dimensions, you just get, once you get above 4 dimensions.
That's a rabbit hole.
It's limited.
I need to go down. I need to check that out. Right, next.
I'll just mention another video so that I've got it on my list of things to give to you for people to check out. It's a number file video. I wrote down the name earlier. Perfect shapes in higher dimensions from number file.
Higher dimension.
which is essentially a much better explanation of everything I've just been trying to say, with like wonderful computer generated graphics and these fantastic wireframe projections that this professor has made with a 3D printer, I assume, to illustrate what these
that
high
sounds
dimensional states mean. It's
Would
amazing.
you have a 3D printer? I know that.
Oh, indeed.
I would definitely be making some platonic shapes like the first week. That'd be my first project. Start with them and work my way out. Right, next. This dude. This is the best picture I could find of him. Look at like I don't know if he actually looked like this. Like maybe the artist didn't get on with him or something, and he was like, "I'm going to make you look crazy." But he's wearing a t-shirt on his head, and he's looking pretty dapper. Anyway, right, who's this dude, and why is he important?
So this dude is Leonhard Euler, to give him his proper pronunciation, I hope. That's what I was told is the proper pronunciation, but you get people saying Euler, Euler.
You're right. I got this wrong the other day, and my friend was like, "Don't get it wrong," and I just messed it up. You're right. The phonetic is Euler.
Yes.
Yes.
That's what I've always been told. That's what I run with. That's what I think when I see his name. So Euler was such a boss. Like I can't even describe. He did so much. So he did a bunch of cool stuff that's a bit less known about geometry, where there's this wonderful super simple equation that's just like E equals V plus F plus T or something, and it's a really nice thing about shapes, which I've only seen relatively recently in a video, so I can't really remember any details of it, but if you look him up you'll find it, I'm sure, and it's super cool. But the more famous thing is, as you have just put up, Euler's formula and Euler's identity. So the famous one is Euler's identity, that e to the I5 plus 1 equals 0, because it's this beautiful relationship between these 5 fundamental constants, these things that are super important to maths, that have seemingly some kind of cosmological importance. Like, if we ever encounter aliens, I think those 5 numbers, that identity, could well be one of the founding building blocks of communication between us.
Oof. Right, hold on.
That's how fundamental I think this identity is to the universe.
Mate. Right, hold on. Let's go back a second there. If we meet aliens, you think this formula? Why is this formula so important that you think it will be like involved somehow? That's cool as fuck. Why do you think that? Why do you think that?
So you've got to look at what makes it up. You've got E, you've got I, you've got pi, you've got 1, and you've got 0. Let's start with 1. That's the easiest. It's the additive identity. The multiplicative identity. 0 is the additive identity. What that means is you can times anything by 1 and it stays as it is. This is a group theory thing, having identities and stuff. Any group, I think it is, has to have an identity and a bunch of other stuff. So all groups are sets, but only certain sets are groups, and they have these certain properties. So these are like kind of important numbers in the group of numbers. So 1 is the multiplicative identity. If you multiply anything by 1, it stays the same. 0 is the additive identity. If you add 0 to anything, it stays the same.
Okay, yeah.
I is the imaginary unit. That's a bit more of a weird one, as is E. I'll come back to pi first, because that's a geometrical constant. That's the relationship between circles and lines. And I feel like anybody who will ever have a chance of getting to interstellar travel or interstellar communication will have worked out that there is a link between circles and lines in them.
Sure. And then probably hydrogen, right?
Yeah.
Is am I right in thinking like number 1 would constitute like the idea of hydrogen to an alien? Because it's like the most abundant thing.
I think there's a bunch of like. I think there's a good chance. There's a decent chance that would be the case.
I know it was kind of like, I can't remember exactly how they inscribed it, but on the gold disc that went up on Voyager.
Yeah,
2,
they have the symbol of the nucleus in the single electron orbital.
Right, and so that's to represent hydrogen, right?
Yes, and it's just basically to say we understand what an atom is. We understand that this is the most basic building block of the universe.
Yeah.
And to just be like, this is the kind of level we're at.
And so you think if they strap this equation on that gold disc, this would be easier for them to understand, or they might be like, oh look, they've wrote that equation down too. How cool.
Well, they wouldn't write it down in the same way. These things wouldn't mean anything to them. You'd have to get to a point where you could like have some kind of translation going. So it wouldn't be the very first thing. Things like 1 being a single unit of something would probably be the first thing I would imagine. Things like hydrogen being schematically represented like that, I think that's quite fundamental. And then once you've got a bit of symbolic thing, once you can understand that we're talking about numbers, and once you know that we both have an understanding of what numbers are important in the universe, you can go e to the I pi plus 1 equals 0. And hopefully you've worked out what 1 and 0 are. You might have an equality sign. And from there, if they've got that in their culture, I reckon any mathematician would probably work out that if, given the context, something and 1 equivalent to 0, that's got to be Euler's identity, right?
Well, they won't know Euler, will they? The alien will be like, I mind that Euler guy from planet Earth.
They'll know it as whatever they decided to name it as, whether that's after a member of their species or they have some more esoteric or abstract convention for naming things.
Maybe Zoidberg or something like that.
Yeah. So you've got I, which is the imaginary unit. So that's a slightly more kind of arcane area. So that reaches back to numbers and number theory. So I represents the numbers that are not the real numbers, the numbers that we can't immediately think about easily. So, oh, that looks like a fun image. It's not quite popped up on the big screen yet. I'm guessing that's a schematic diagram of all the types of numbers. Yeah, that's good stuff. So, yeah. So all numbers, it's a really good diagram. So all numbers are complex numbers indeed, because complex numbers are the mixture of the numbers that we're familiar with and imaginary numbers. So the way to kind of think about imaginary numbers is essentially it's to do with square roots. So I'm sure we all understand that if you multiply 2 numbers together that are positive, you get a positive number coming out. That's nice and easy. If you multiply 2 negative numbers together, you get a positive number coming out as well. If you multiply a negative and a positive, you get a negative number. But that means that all squares, all numbers times by themselves, have to be positive. Or at least all real numbers times by themselves have to be positive. Because we start getting things. Yeah. But once we get into algebra, we start getting things like the determinant of certain algebraic equations being the square root of a negative number. And we would assume that these quadratic equations mean just as much as their counterparts that don't give this crazy, weird, scary negative root determinant.
Yeah. So it just gets a bit squirrely.
Yeah, it just gets a bit weird. People were just like, oh, well, that's a non-physical solution. That's something that doesn't mean anything in reality. Until Euler came along and was like, but what if it did?
And so he wore his green dressing gown and he was like, by the way, guys, I've got this idea. And like, how do you think he would have how do you think he brought it to, well, do you know much about that? Like, how did he bring it to the scientific community and how was it received? Like, did folk get it straight away, or was he like ostracized like most people are as soon as they like yeah?
I think he was pretty much recognized as one of the greatest mathematicians of his time at his time. because like I say, he did so much other stuff. This is just one thing that he did, and he was super important in a whole load of stuff. But it was in the 1850s or something, so he probably used language that he would have been speaking Dutch or whatever people in that area of the world were speaking at that time.
Sure.
And it would have been some kind of archaic form. So I don't know how he was portraying it to people. But I think essentially the idea is that once you've got the idea of a negative root, it's like, or the root of the square root of a negative number, it's like, why not? Why not use that? But it took kind of a leap of genius to kind of push through that barrier of non-comprehension.
And he's like, okay,
Euler's stroke of genius was just to be like, well, what if this was a thing? What would the simplest one of it be? The square root of -1. That's the smallest number. It's the simplest number. It's the multiplicative identity. When you've got 1, if we have the square root of -1, that kind of feels intuitively like it's probably something fairly basic in this new realm of the square roots of negative numbers. So we call the square root of -1 I. And it kind of gives you this whole different axis of numbers. So if you've got your real number line going like that, so you've got 1 in the middle, going off to minus infinity that way and positive infinity that way, I think should be right for the way I'm flipped on the screen.
Yeah.
I hope. Excellent. And then you've got your plus I, minus I going in this direction. So instead of just having a line of numbers, you've now got a whole plane of numbers to play with.
I get you, yeah.
And this is just a new direction in which numbers can go.
Well, how about this graph?
Oh, that's some classic shit. That's good stuff. Is that
because that's kind of what you're getting at, is like, to me, that's like, I mean, the helix being sort of put into a graph form or being like described in a dimension smaller than it actually exists in.
Yeah, kind of. I mean, that's the kind of mathematical route. So that's actually probably what came up first before the identity. That was probably what he was initially talking about. And that again kind of relates back to a whole different area. That's kind of the geometry part of it. That's what pi represents in the identity.
Mm-hmm. And so, can I ask then, because I'm like, I can appreciate how important this formula is, and the fact that aliens would dig it or likely know it already. So like, what are like the implications of that formula for just like a normal person, like living, like going about their ordinary life? Like, how has it impacted the average person, that thing having been invented? I know it's a bit of a crazy question. Do you get what I mean?
Yeah. So I mean, there's all kinds of stuff that it's used in. So the Fourier transform, which is fundamental to data compression that we are using right now.
Right. So we could talk if it wasn't for Euler.
I mean, yeah, essentially, like this is the foundational stuff. The Fourier transform came 50 years later or something from someone completely different, and it was more that this opened up whole areas. So there are a few kind of direct things that it's useful for in mathematical terms and things. When you're writing down things with certain types of trigonometry, it's easier to use exponentials than it is to write out lots of causes and sines and stuff. And it's useful for solving a lot of problems. I'd say that the relevance to your average non-mathematician walking around on the street is probably secondhand at best, because it's so foundational to things.
I like the thought that it's been used in something like data compression. That's something else I'm like stupidly obsessed with, is like neural networks and where AI is and DeepMind and all that sort of thing. And I think
of that math would be possible without this. And that's the thing. It appears in so many places. It appears in all kinds of statistics. Like, I guarantee that any kind of artificial intelligence program will have something relating to some part of this somewhere in it, because it's statistics.
And it's like, okay, here's a question then. Is a formula like Euler's formula, is it And like I don't know, I'm just gonna say it. Is it invented or is it discovered? Like, is it uncovered like a dinosaur fossil? It like is uncovered. It's like there and just waiting to be found, or have we constructed it as a means of like interpreting our environment? Like, do you know what I'm getting at?
I do. It's a fascinating question. It's one that I don't have an answer to, but I kind of feel like if I was pressed to give an answer, I'd say that it's it's like a category error. So it's not either of those things, but it's also kind of both. If that makes sense.
Good answer. It always ends up being a bit of both, doesn't it?
That's the thing. Like, that's why it's such an interesting conversation, because when you frame it as this binary where it has to be this thing or this thing, then and with a question like this, where it has elements of both, you then get people being like, oh, well, I think this element is more important and therefore it's this thing, or this element is more important and therefore it's the other thing. But,
sure. But like, well, if you had to go on your gut right now, like, what would you say?
Neither.
It's that doesn't help me.
There's not a logical way of thinking about it. It's neither discovered nor invented. It's
okay. I hear
worked
you.
out.
I hear you.
Like it depends as well on, like, I think in order to really talk about this kind of discussion, you have to be more precise about your questions. So it depends on. I'm losing my thread. Is it invented or is it discovered?
Well, here we go. Right, let's just put this man's face on the screen, because, like, a man like Einstein, right? Like, to me, it feels like E equals mc squared is probably the most famous formula on the face of the planet, and to me, it feels like that is like a universal idea, which was discovered, but maybe the way in which we interpret it.
I've remembered where my thought process was going. Sorry, it's to do with
Einstein would help.
Reference and existence. So when you're talking about e to the I pi equals e to the I pi plus 1 equals 0, are you talking about the fundamental structure of the universe that we're talking about when we say that, or are you talking about this string of symbols? Because the answer is different depending on which one you're talking about.
Right. So
and obviously there is a discussion to be had about whether or not they are even the same thing, because some people would argue that those are the same thing, and that that's the kind of constructivist view of the universe, I think, where it's everything that exists that we can conceive only exists because we conceive of it. And that although there are relations, like for some people, there are relations to things that exist in the universe, but all we ever perceive of them is our perception. It's our second-hand light bounced off of that thing. It's not the thing itself. And it's kind of the same with mathematics, in terms of it seems to be referring to something that exists in the universe, but the mathematics, the strings of symbols that we use to talk about them, aren't really the thing itself.
Yeah, it's an arbitrary concept as a means of explaining this particular rhythm of life that we have looked at very closely, and we interpret it using these symbols. But yeah, if you went to an alien planet and you asked what their E equals mc squared is, it's obviously going to be a different bunch of symbols, or who knows, they might not even have language, you know. But if they have alien cities with buildings, then you know they've learned it.
They've learned something similar, at least, if they're using any kind of nuclear or
if you can see they're into physics of some sort. Right. Well, let's continue.
So, just to get back to the identity, I just want to speak a little bit about E as well, because E is another of these super important fundamental things.
I'll put the
way it's usually introduced is that it's the number for which the expression y equals e to the x. You take the gradient of that line that you get from drawing that, and it's always the same value as x as y at that point, which it's a bit of an abstract thing. The gradient is the same as the value you get out of the equation, but it's super important in a lot of like calculus and integration stuff, and that's why you get things useful coming out of it, like the Fourier transform, which is an integral involving things multiplied by e to the ix. So again, it's involving all these separate bits, but Euler's identity is just kind of the simplest way that all of these fundamental and apparently disparate numbers link together. So you've got your multiplicative identity, your additive identity, your geometrical constant, your imaginary unit, and this thing that's fundamental to gradients and rates of change.
Yeah.
And there's no clear, obvious reason why they should be linked in this fundamental way, but they are. And it's kind of beautiful. And it's that same thing, if a civilization has got to a certain point, they're probably going to have realized this. So although it's not one of your first building blocks of communication, it's going to be an important one, because it's where you start to be able to push out into the further realms of how you symbolize things and where you're at with your understanding of the universe, if that makes sense.
It's kind of like what you're saying is like, it's almost like scientific poetry. It's almost like, wow, I can't believe these things actually fit together like this.
That's a really good analogy, actually. Yeah.
Like,
yeah, that's really good. I've never heard that before. But yeah, that's spot on. It really is like poetry.
A lot of science, I find that way, is like, and I guess that's what I was getting at as well, is like, was it discovered or invented? And like, I think the same about music. I'm like, I mean, think of an amazing song like Purple Rain, right? I feel like was Purple Rain always going to be written by somebody? Or, you know, maybe Prince is a bad idea, a bad example, sorry. But
Ode to Joy. Let's take something like the you know,
right,
super simple melody
like that. Yeah, it's a better example.
You do feel like it had to have been written at some point if you have a 12-tone equal temperament system, right. Or there would be an equivalent in any other tuning system that you could draw some equivalence between.
Yeah,
that's like just it's obvious you're going up and then back down.
Or like Seven Nation Army. Like Seven Nation Army.
Yeah.
Like
on the water.
There's a statistical likelihood that a simple melody like that is inevitable, and perhaps is discovered, not invented.
But that's only if you're using a 12-tone equal tempered system, which isn't fundamental to the universe.
And there's
if you were using a 42-tone equal tempered system, you'd have a completely different set of things. And like I say, there might be some kind of like mapping between them that you could make sensible. Like the equivalent to Ode to Joy goes up to starts on, what would it be? It'd be like 12 or something, goes up to the same fraction of the scale that Ode to Joy goes up to, and then goes back down.
Mm-hmm.
And that's the same kind of idea in that 42-tone equal tempered scale. But there's nothing fundamental that says you have to always have the same number of divisions in your scale. Whereas I think the thing about things like Euler's formula is that you're talking about the same fundamental things. It's the logical building blocks of existence.
Yeah, and I think that's the most fascinating thing for most people, and I think that's why certainly geometry and things like that are so much more accessible, and like people enjoy watching things like this because it's like everyone understands a triangle, but like the story of that when it's connected to all of these formulas and like the building blocks of like science and life, as you say, it's like I just find it so crazy fascinating.
And all that cos and sine stuff that links back to E, as we saw earlier with the formula that the identity comes from, that's all triangles. Cosines and sines are just from right angle triangles and how they interact with, like how they fit into circles, essentially.
Yeah. I'm going to add up, I'm going to put this back up here. Here we go. Right. I feel like we've achieved Euler pretty well. Not Euler, Euler. So I know
you're going to say something about Einstein, right?
I just had to put him in that folder of pictures because it just didn't feel right to not have him there. So he did his job. It helped to jog your memory.
He did.
This
Put
image,
back on my train of thought.
This is probably one of my favorite images in in the entire universe.
Is
And
that the deep field?
this is the deep field. And
you know, there's been 2 more since then. There's the ultra deep field, and I think there's definitely been one more, the ultra deep field that exists, and I think there was another one since that as well.
Ooh, that's not definitely not the third one. If that's it, I'll need to have a look for that afterwards. Right. So I know you feel passionate about this photo too. So right, just tell me, like, here's the photo. Just tell me how you feel about it and what, like, why you like this photo too.
So I think the most important thing to think about with this photo is that when it was taken, they thought that they were getting a picture of black emptiness, of nothing. The whole point of choosing that particular bit of sky was that at the time, it was the darkest bit of sky they could image. There was no stars. There was nothing visible to anything that had looked in that direction up to that point. So you get this, expecting to see nothing. And it just expands the universe straight away. So at this point, we knew that there were other galaxies. We knew that we weren't alone. Our galaxy wasn't the only thing in the universe. We knew that there were huge gulfs of space between us and, for example, Andromeda, the nearest galaxy. Edwin Hubble, in fact, was the guy that worked that out in the 20s. More recent than you might think, more recent than I thought when I found that out. We didn't know that there were other galaxies until sometime in the 1920s. It's pretty mind-blowing.
That is absolutely mind-blowing, that fact. Right? 1920s, like, to think, like, to be so closed off from that knowledge is kind of like scary in itself. Like, and then, like, the amount we've had to absorb, even in the last 10 years, like, to keep up with space and technology and what it's showing us as we start to throw our instruments out there and get these crazy results. And like, this one was, for me, like, who was into space a lot and keep up to date with since I was a teenager. Like, when this came out, it just, like, I almost couldn't sleep because it was like my mind was just racing with, like, wow, like, look at all those like, those are galaxies. Those aren't stars. Like, each of them is an entire galaxy, and that was in a dark
2 stars that are actually visible in the original. There's one that you can see. It's got a little star-shaped bit around it. It's in, like, the bottom right-hand corner-ish, just up from the bottom right-hand corner. And there's another one somewhere that I can't remember where the other one is. But the rest of, everything else in that image, and there are thousands of objects in that image, is a galaxy.
And that was a pinprick. It was from a pinprick of black. That's crazy.
Yeah.
And so this picture here has got an idea of, gives you an idea how far back we're looking, right? So you got one at 0.55 billion years. I believe that's Andromeda, actually. I've got another cool picture of Andromeda within the deep field, which is quite cool. And then we kind of go up in the year, so 2.7 billion years up to 5, 10, and then 13 billion. And I guess we think what's the universe is 13.8 roughly billion years old.
I think it's gone up a bit since then. I think the last number I knew was 14.3.
Wow. Okay.
Something to that effect.
It's funny how that, because that, you'd think with all our constants and our maths, we'd have a good idea of that. I've got another question about that later.
We've got to work out the age of the universe is the Hubble constant. And going back to Hubble, he was another fucking giant. But yeah, and we don't really know the Hubble constant because we need to basically exist across a far larger area of space than we do in order to accurately measure it.
Yeah, I've heard of the discrepancy between, basically, the Hubble's constant is what we're talking about is the speed at which the universe is expanding, and like I think some people had it at like 13.2, and other folk had it like 14.1. There was like different results coming back from the LHC as was coming back from Hubble, and even I heard some theories that like perhaps the universe is expanding in some places quicker than others, and it's not a uniform spread. And it's an interesting idea. What's your thoughts on that? Like,
well, that's a big question. What are my thoughts on inflation? I mean, one of my favorite things about the Hubble Deep Field and just looking at the sky in general is that you're looking back in time.
Yeah.
That the light that's hitting your eyes from a star was emitted maybe thousands of years ago, even for stars that are near us. And yeah, like if you're looking in the deep field, you're seeing things that were emitted billions of years ago. That photo is looking back into the past, and I find that pretty mind blowing. And then I guess there's just like the size.
I like the thought experiment of if you had a telescope good enough and had a faster than light travel vehicle and could travel out into interstellar space and go far enough that you find a planet which is I don't know, a few million light years away, and then you sit there and you've got your telescope and you look back at Earth, and your telescope's so good for some reason you can see right onto the planet's surface, and if you were to look back from the correct star at the right point, you'd likely see a dinosaur. That's cool.
Like, that is very cool.
There might be an alien planet right now who are looking back from one of these galaxies from the Hubble Deep Field who are like getting a pretty awesome view of our like primordial Earth getting created.
And that's the thing as well. Like people talk about the Fermi Paradox as if it's weird that we haven't seen other life in the galaxy or in the universe, but it's entirely possible that just everywhere that we've had any light from, the light that came from there happened way before there was any life there. Like there could be civilizations as old as ours that we won't get any hint of for billions or more years. You know, there could be civilizations in areas of the universe that we will never see because it's expanding too fast and light will never reach us from those areas, the unobservable universe.
Well, I like to think that is like the Fermi Paradox that I understand is like the chances of life are quite high, but the chances of life existing at the same time and us having the technology to detect each other. Like, I don't know, the graphic for this show where you see that sort of radar blip go out from the Earth. If you imagine one of those goes out maybe every billion years out into space and might be picked up by somebody. Like the chances of another planet being at that same point and their little radar blip goes out and us being able to bridge that distance and time, and it just the odds are so small. So I'm going to do an alien special. I need to do it because like I'm deep into aliens and like there's crazy things that I can't explain but with the idea of this Fermi paradox and the such a small probability of things actually being able to get here unless they have technologies which are way, way, way beyond what we think is possible or out with our physics and things, you know, it's not going to happen.
Exactly. Like, yeah, we need... I don't know if it's entirely impossible. Like, the Alcubierre drive is a sound idea, I think. And wormholes are permissible by relativity.
Yeah, that's crazy, isn't it? Like, that's actually one of probably the easiest ways for us to actually approach the idea of going
I think
further.
It's one of the more plausible ideas for having any kind of spread of humanity beyond, like, you know, a few nearby stars.
Here we are. So I think from here we can quite easily segue to black holes. The thing, like when you're a kid, like the thing, like I remember in my primary 3 class, Miss Lawrence was her name. She got the janitor to come into class one day with this weird looking metal object with loads of symbols on it and things, and the janitor was like, don't know where it came from, and just like sort of fell out of the sky. Isn't it strange? Maybe it's come from a UFO. And anyway, like that's all it took. We were all like hooked straight away. And then obviously the next coolest thing besides aliens to get kids interested in space is black holes. And like they're just cool. They just boggle the mind. The singularity, like what would happen if, and like then like the experimentations and mind experimentations you can do with them are great fun.
I mean, one of the things I love most about black holes is that they're one of those things where the more you find out about them, the more baffling they are. Like, just the more, like, and that's beyond, far beyond anything that I can talk about, because I've read and spoken to people who have much more understanding of this kind of physics than I do, and they've said the same, that just the more that you find out about it, the more utterly bizarre and crazy and weird it is.
Yeah.
And you get things like the information paradoxes and time going backwards once you pass the event horizon, and all these crazy predictions that, I mean, some people would say they just mean that our maths is not able to, or our theories aren't able to handle it, which I think is a fairly reasonable interpretation, but also it doesn't do much good, if that makes sense. Like it doesn't go anywhere.
It's good to know that we don't know some stuff, though. It's humbling. It's like it's
Oh,
good
absolutely.
to be presented with something like this, which is like we know it's there. Like it's not a lie. Like these things exist. We've even, in fact, we've photographed one now. I've got that photo here. Hold on, let me find it.
That's a good
Oh,
thought.
sorry, that's you. Here it is. Zoom in on it. So we actually photographed this not too long ago. I was really excited when this happened, and like I'm a absolutely huge Lord of the Rings fan. Like I love Lord of the Rings, and I was like, oh my god, it's Sauron! Like it's real.
It's actual Sauron.
But that's a black hole, and then so what's that glowing stuff around it? Why does that happen?
So that's the accretion disk, which is essentially matter that's falling into the black hole, and as it falls towards it, it gets so much energy from falling in, it goes so fast that essentially things start to collide and glow. It's basically the same kind of processes as would be going on in a star, just being caused by the conditions around the black hole rather than the intense gravity in the core of a concentration of mass that big.
And then occasionally, I think we've seen in that other thing, it can spit out stuff at a crazy rate too. Now is it turned into a pulsar at that point, or are pulsars different? Are they those are stars that have collided? Is it, or what's the distinction between that ray of
pulsars? I think are a type of neutron star, if I recall correctly.
Yeah.
Which, because of the way it's spinning, will. Thank you very much, love. Tess just brought me some water.
Hi, Tess.
So extra water, I should say. She refilled my bottle for me. So yeah, a pulsar, I believe, is a specific type of neutron star that, because of the way it's spinning, will, at a certain interval, shoot out a jet of high density, high energy radiation and matter.
Yeah, and that's like one of the most, like, I think they're one of the most reliable timings on, like, that we use now. Pulsars are so, the rhythm of it is so precise and so predictable that they're even more accurate than some of our clocks on planet Earth that we've managed. Nuclear clocks and things like this. I might be talking out my ass.
It's not a statistic I'm familiar with, but I could believe it. I know that there are some really mind-blowing things that happen with those kind of things, and because they're going so fast and there's so little happening to prevent them, like the kind of time periods over which they change are incredibly long. So it would be I can believe that it would be very, very consistent for a very, very long time and not change perceptibly in that time.
Yeah, I know that because I think a lot of the signals that maybe were rather excitingly interpreted as aliens at first turned out to be pulsars because of their regularity. and the way they showed up on graphs and things. Did that? Sorry, bear with me a second. Get a rabbit, they said. She's eating everything. There we go. There we go. So this well, I can't even say it. Relativistic jet. So that's different from like a pulsar, like streaming out like light years into, like, because I know pulsars they're bigger than even entire galaxies sometimes, to how far they go. But this is more to do with the accretion disk and the heating up of the energy of the particles going around.
So I don't know about the jet for a black hole, because I know that, again, it's something to do with the fact that it's spinning. And the accretion disk is matter that's falling in, so it's about to go through the event horizon. I think the jets that come out are actually separate from the accretion disk, and that they're a separate process. But I hold my hands up. This is not something I can speak with on any authority. Speak on with any authority, because I am not a black hole expert. Essentially, I think unless you've really
well, if you find one, you're because of you might come across somebody that is an actual black hole expert, and they've spent years. If you do come across one at a festival or in your life travels, put them in touch with me, and we'll do like a specifically black hole special, because they are the most like thought-provoking thing. Like, they really get the mind going. Let's get some more pictures up here.
So one of the really cool things about black holes is, as with all of relativity, is the idea of time dilation, I think. So it's the idea that depending on how fast you're going or what the curvature of the space-time is where you are, you'll experience time at essentially different rates. So things that are falling into the black hole, we from outside see them fall in past the event horizon, but from their perspective, as they cross the event horizon, according to all of our theories, as far as we know, time from that reference frame falling into the black hole stops when you reach the event horizon. So what that means for
there, you just see them stuck there.
Well, no, we still see it fall in. The only perspective from which time stops is the perspective of that particle that is falling into the black hole. So if you were falling into a black hole and you were somehow able to retain consciousness despite the spaghettification and the immense tidal forces millions of light years out, if you could actually still have a nucleated consciousness as you pass the event horizon, as far as we understand, you would experience time slowing down. You would see the rest of the universe pass by.
Whoa!
As you fell into that black hole, so you would never see anything else other than the black hole and going into it. But in that instant, it's hard because reference frames are weird and relativity is weird.
It's a very hard thing to talk about without visual aids and things. I appreciate that.
And without maths as well.
Here's a question I had. I had this thought in the shower when I was thinking about black holes, which is similar to what you were saying there, but like your perspective there was seeing someone fall into a black hole. I was trying to figure out what you would see, like if it was me, right, from my perspective, and I was falling backwards from a rocket ship into a black hole, right? And my perspective, if I had my hand out, like, hold on, I'll take this off for a second. If I had my hand out with a watch on it, right, with a time on it, or with a second clock going by, and I held my arm out like as far as I could away from my eyes, and so my head would be entering the black hole a few seconds before my watch did. What would happen? Would the hand just stop, the like second hand, or would it speed up really quick? Like, I was trying to figure out what might happen from the perspective of the person falling in.
That's a good question. I'm not sure if I can actually give you
It's a weird one, isn't it?
Answer. It is. So, as I understand it, time from your perspective of your head is going to be going slower than in the reference frame of the watch on your wrist. So you would see the clock going faster as you move towards the event horizon.
So it would speed up,
So,
right? That was my gut instinct.
I think that's right.
Well, let's go for that for now, and then we'll try and confirm it. I can.
Yeah, that fits with interstellar travel as well, because if you're going near the speed of light, time passes slower for you. So an 80-year journey near the speed of light would end up being much longer for the people back at Earth.
Yeah.
Who are
that's
moving.
One of the things that Interstellar did really well, the film with Matthew McConaughey, where with the time difference and time dilation and then being near the black hole, that really, I love that movie. I go back and watch that every year almost religiously.
So yeah, that anything that they illustrate, if they've got it right in that movie, I don't think I didn't see that one. I saw The Martian, which I can't remember at the time.
Yeah, The Martian, and I mean they're fairly well rated.
I think
a lot of the science is quite dramatic.
But yeah, if they've got the science right, and you want to think about the going into the black hole, you just take those thoughts to their logical conclusion.
Mm-hmm.
So the logical conclusion of time going faster for the clock on your wrist is that the rest of the universe goes by and you see the end of the universe before you fall into the black hole. And yeah, you get some paradoxes here.
So you would see the end of the universe.
What happens
you think
if you were still conscious and able to perceive? I believe that is the idea.
You're right, man. So if I want to see the end of the universe,
time for your brain as it hits the event horizon is going at an infinitesimally slow rate. So compared to the rest of the universe. So that means that everything else in the universe is going much faster than it is for you.
Oh. Man, this is hurting my head. That's crazy. So like the restaurant at the end of the universe, like you just jump in a black hole. That's like essentially that's like what that book's about. It's like
if you can hop back out again, you find the restaurant.
Yeah. Right, I'm off to find a black hole. Like I want to see the end of the universe.
That said, depending on how long it takes for the end of the universe to happen, and depending what happens in the meantime, that could be where the restaurant at the end of the universe could be essentially infinitely far away from where you are when you hop out of your black hole.
Oh,
because space expanding and stuff.
Good point. Right. Well, here's the thing. I've not got a picture for this, but we're nearly about time to wrap up. So we'll talk about this a bit, and then we'll do some more comments and all that, and then we'll wrap up if that's all right.
Mm-hmm.
Now, have you ever heard of a thing called the Boutet's void?
Yes, I have.
So the Boutet's void, for people that don't know, it's really there's a great little 20-minute video on it by a guy called SEA. I'll put a link as before on YouTube. He's a really, really young guy, and he's just really very clever with his words, kind of like Neil deGrasse Tyson, in explaining things. But he does this video on the Boutet's void, and it's the largest void of space that we've found, like way bigger than any other void. And I mean, there's the reason it's kind of famous is there's lots of crazy theories as to why this vast expanse of nothing exists. One of the more crazy theories being that there may be like a super advanced like category 4 like civilization which is like working their way out from the center and slowly consuming the stars, and like we've not seen any of the stars at the side of it go out or anything yet, but if we do, it might be a bit worrying. How does something like that like happen? Like what's your thoughts on how it formed? Have you thought about it much?
I mean, not a huge amount, if I'm honest. I quite like the theory of it being like a sink for a parallel universe.
Ooh,
I think that's pretty cool. Like the idea being that it's kind of an area where our universe is like overlapping a bit with another universe, and that has some relation to the darkness that we observe there. I like that also ties into a theory about why gravity is so much weaker compared to the other fundamental forces, which is also that it could be leaking out into parallel universes. I also I find it fascinating to think that it could be a technological thing or a non-natural process. Or, I mean, I think the most likely explanation is that it's just the same as any other void, and just by chance it happens to be the biggest one. Because all of this stuff, all of the fundamental structure of the universe was kind of to do with asymmetries and inconsistencies in the very early universe. So again, it ties back into like the antimatter and matter asymmetry as well. Why does matter exist? Why didn't it all annihilate with all of the antimatter? Why was there slightly different amounts? So you start off with these little inconsistencies and inhomogeneities in the early universe, and then through time and statistics and expansion, they turn into the kind of large-scale structure that we see today. And we have structure that's far bigger than the Booter's void. We have superclusters of galaxies and things like that we've identified. So if you can have structure in such large scales, to my understanding, I can't see any obvious reason why you couldn't have non-structure.
Certainly.
It's foreground and background, isn't it?
Once you zoom out enough and you start to even see structure within the filaments of the galaxy, of the universe, sorry, and the way galaxies sort of form these filaments through, it's kind of weird when you zoom right out. You watch these videos where they sort of try and deal with the scale of the universe, and
I do like those videos.
I probably that's when I'm just like my head, oh my god. There's a good like sort of sister video of the Boute's void one called The Loneliest Planet. And I guess that's why it got me thinking so much, because like it kind of describes what the experience of living on a planet within the middle of this void would be like, and how you would not even know there was a universe out there because none of the light would reach you, and it would just be the loneliest experience like ever. And not only that, then he starts to talk about like rogue planets which have drifted off from solar systems or been thrown out, like there might be solar systems with big huge planets like Jupiter with huge gravity that just go like, sorry, bye, see you later, planet.
Off you go.
And so they'll literally just are out in these gaps between the filaments, even just floating about. And I like to think maybe like there's some sort of like frozen bacteria on this moon or whatever will get heated up and like re-enter a solar system millions of years later. And like it'd be like true aliens, like you traveled all this way in hibernation and then you kind of get thawed out and join another solar system.
Basically the plot of The Expanse, right?
Well, I don't know. I'm quite far through. I don't know if that's like a conclusionary thing or
it seems to be what they've implied so far, I reckon.
Pretty much, yeah, I would agree. Like, I'm on Nemesis games at the moment in terms of the books.
I haven't read the books yet. I've just watched the series.
I love it, man. In fact, weird factotum, Whistling in the Dark is named after a quote from the books, where Admiral Avasarala is talking about James Holden when he's out doing a spacewalk and he's like sort of muttering away, telling crazy stories. And she's like, his girlfriend's like, "What are you doing? Why are you talking away?" Because he's nervous. And Admiral Avasarala, I can't say her name properly, was like, "He's whistling in the dark." And I just thought it was a nice sentiment. I was like, yeah, but like we all do that. We also like hum something or whistle something when we're feeling a bit weird. But then obviously DARC, D-A-R-K was taken, but D-A-R-C is the acronym for Data Radio Channel, as it turns out. So I was like, perfect.
That works.
That's going to do. But yeah, The Expanse is one of my favourite stories. I'd actually recommend I don't like listening to audiobooks all that much because like if the person that's reading it doesn't have a good voice, or I don't find them interesting. I just can't listen to it. But the guy that reads The Expanse audiobooks is amazing. He's very, very good at doing the voices, and it weirdly is something I came to having seen the TV show and then gone to them. So like a lot of the world's been created for me. Like half the trouble with books sometimes is you're creating that world, and I can often sit and like I'm just trying to get the set right for how I want it when I'm reading a book or something. But a lot of that was taken away, so I could sort of just really enjoy the story. So if you enjoy the TV show, grab the audiobooks, or I can send you them if you want to listen. And yeah, the story's getting, oh my god, it's going, like the next 2 or 3 seasons are going to be so exciting. They've got a lot to pull off. Right, so what we'll do is we'll get some more comments up. If you've got any questions right now, if you're still watching, thank you so much for watching, and we've really enjoyed this tonight. You've blown my mind, Ben. Yep, we're coming on again later at a later date, and we'll do this again.
Man. Talk about some more quantum stuff next time.
People been enjoying this. Talk about what, sorry?
Some quantum stuff next time.
Oh yes, please, quantum. That'd be good. I knew we had a lot to tackle today, but you know what? I think we've done pretty bloody well to get through.
We got through a lot of stuff.
Yeah. Right, Lisa Shaw. Anybody else got a headache? My head hurts a little now. There's Gemma. I'm hoping Gemma's going to come on and talk to me at some point. She's got lots of different things she's passionate about. I think she'd be great to have on the show. Sam Barnes. Mycelium root of I don't know. The flower of life appears in so many places. So we've got more stuff here. Right, is anyone like? If anyone's watching, type a question. Let's get at least one question before we wrap up for the evening. Could be anything. Doesn't even have to be space related. Here we go. There's my mum again. And Alex. So Alex is coming on Thursday night. So we're just going to have a laid back chat. We're into a lot of the same things, and just shoot the shit and see what's going on. Give us a second. Would you also too? I wanted to ask just your advice, even like the other part of this show, Ben's the news from the void, and I want it to be more interactive, and I want it to be a place where, like, no matter what sort of opinion you have, whether it be quite far left or far right or somewhere more centrist, like the point is, like, opinions can be had, and you're not going to get sort of like judged or hopefully not get targeted if you come on and express a view which you're passionate about. I'm going to try and direct them at like specific topics and things and that. But I mean, is there things that are happening? Obviously, the world right now is crazy, and everyone's got their own opinions, and everyone like. Do you think that that's a good idea to have a space like that for people? And would you be interested coming on and giving some of your views on more of the political side of things?
I'd certainly be interested in coming and chat to you about political side of things. It's a tough question because obviously no one wants censorship, and no one wants to do the thing of just saying, "Oh, that idea is so stupid; it never needs to be discussed." But also, I feel like we are kind of past the point of a lot of things. Like, we shouldn't be discussing whether slavery is okay, for example, kind of obviously. And I think that there have to be some limits. I don't think you can, with good conscience, have that very absolutist view of all views are equally valid and should be given equal amounts of time.
Yeah. No, I think that's the tightrope, isn't it? It's like I feel a good way to put it is like, if you're willing to come and talk about whatever it is that you're wanting to talk about, and you're happy to agree to talk about it reasonably, and even if you if you do feel very, very emotional about something, then I mean, me as someone talking to someone who is obviously way more emotional about a topic and wasn't seeing reason, Like, I don't want to cut that person off or say, no, even though you're very emotional, that point of view is rubbish. You shouldn't think that. Like, there needs to be a little space between, like, well, okay, your view is very crazy and I disagree with that potentially. But the fact that you feel so emotional about it means there is a conversation there to be had. And so I guess I want it to sort of land in that space, is like, still be open, but like, I want a little back in terms of, like, let's be reasonable to each other and civil without letting it descend into like a Facebook comments thread where folk just go fucking crazy and say things they don't actually mean, or defend a argument which isn't even theirs just because they shared some article, and they get defensive because someone's like, why do you believe that? And it's like, well, you can share an article without it actually being beholden,
without it representing your fundamental worldview. Yeah, absolutely.
Exactly. And it's just been really getting to me. So, like, yeah, I mean, I appreciate your point of view a lot, man, and I know you would have good opinions on some of the things I'm planning to talk about. So, yeah, I would really appreciate if you'd come on to the news show. I'll let you know when they're happening.
Aye, man, for sure. Yeah, like I say, certainly interested in that.
Wicked. Right, we've got some questions, dude. Right, here we go. Ooh. Hell yeah.
I like questions.
One from Sam. Do you follow Nassim Haramein at all? Is it Haramein?
I've seen a few bits and pieces from him. I've got to admit that what I've seen struck me as pseudoscience. It didn't seem particularly well-founded. It was making a lot of extravagant claims and not really backing them up with anything that I could put my finger on. I tried reading a couple of the papers that I saw linked, and I just wasn't convinced.
Fair days. I'll need to have a look into that. I've never heard that name.
It does a lot. I think the thing that I looked into in the most detail was a claim about, essentially, it was something on the level of quantum relativity unification done by some very simplistic geometrical argument. And it kind of looked good at first, but there was no meat to it. There was nothing underpinning it. It was a nice little idea that seemed kind of intellectually pleasing, but had no substance.
Here we go. Seeing the great Benin. He's saying, fair enough. Resonates for me. I've got another question from Alex here. If the universe is both infinite and expanding, what is it expanding into?
So there's a lot to unpack there.
Let's do it.
If the universe is infinite and expanding, then there doesn't need to be anything for it to be expanding into, because it's already infinite. And as we were talking about earlier, infinity isn't necessarily a fixed size. But aside from that, there's just the fact that if the universe is infinite, there's nothing outside of it. And for the way expansion works, you don't need an exterior. It's just the things are getting bigger, the gaps between them are getting bigger. Everything is expanding. The size of an atom is expanding. You're expanding at a rate far too slow to ever notice. But if humans exist several billion years down the line, we'll be a bit bigger because the universe will have expanded with us inside it.
Whoa.
So it's not that there is like this blob that's getting bigger into some external space. It's that there is this thing that is just expanding. It's a good example of it is if you get a balloon and you blow it up a little bit and you draw a bunch of dots on it, and then you blow it up some more, the things get further apart, but
it's almost like stretching into itself.
Yeah, there's
no, that's a good analogy.
More of an analogy for a slightly different thing. That's to do with whether or not you're the center of the universe, because we see things expanding away from us in every direction, and that's what that's illustrating. Sorry, I'm mixing up my illustrations here. That's my bad.
Oh, right, I got one more question, and here we go. I've got a feeling this is from my dad on my mum's Facebook account.
Ooh, superconductors and new batteries and things like that. Let's talk about them next time, because I did a bunch of my master's thesis was simulating hydrogen in extreme conditions, looking for phases that seemed like they might be metallic, because metallic hydrogen is predicted to be a high temperature superconductor, which is baffling and mind-blowing and wonderful.
Yeah, right. Yes, that deserves that. Right. Episode 2, Ben Trolley, we're going to do quantum physics, superconductors, and we didn't talk about Zappa either, but Ben plays with Pygmy Twilight, and it does some awesome Zappa. So, Ben, thank you so much for being my guest tonight.
Absolutely pleasure, man. Thank you for having me. It's not often I get a chance to chat for 2 hours solid about things that I love in this particular area. So yeah, I'm absolutely chuffed.
Well, thank you very much, man, and I look forward to having you on again. Peace out for now, dude.
Peace out, man.
Okie dokie. Right, so thank you, Ben. That's episode 2, the deep dive, done. That was good fun. Hey, Starbuck. Say hello to Starbuck. She's like a dog. She's lovely. I love her. So next up, we got Alex Weir on Thursday. Also, I have on Saturday, the 4th of July. So I'm going to start talking about this now because I'm like, it's kind of blowing my mind. This guy called Timothy Allen got in touch with me shortly before my first show. And started telling me about all this Mayan stuff. He's saying, I've worked on this for 13 years. He started sending me emails with his life's work in it and a book which he has written called Diary of a Dead Conspiracy Theorist, Theories on Time Travel, and then a word I can't actually say. Anyway, obviously my mind's like, whoa, this is crazy. It's pretty cool. Talk to him, and like he's a really nice guy. He lives in Poland. And I was really struggling to get my head around a lot of this stuff. I don't know if it's founded in truth with maths and things, because hopefully some of what I learned tonight might help. Regardless, we're going to get him on, and he's going to tell us all about it, and we might find out how the Mayan calendar's been reinterpreted by Tim, and we're going to talk about just have a conversation with him and see what's going on. I'm going to share some of his stuff on my Facebook page tomorrow, just for you all to look at some of his work and the symbols and the Mayan stuff, and it's just really cool. And kind of it fits in with the sacred geometry stuff we were on about tonight. So that's going to be good. And then something else on the horizon, an amazing person I've been put in touch with called Patrick Tyranny. My friend Alana put me in touch. Now, I talked to him briefly on Skype the other day. I've never met the guy. I just literally talked to him on Skype the other day. He has this amazing story about, he was over in Peru and he was studying plant medicines, and he was doing specifically, I think, Cambo frog ceremonies. And there's a frog out in Amazon in Peru, I believe he was in, the Cambo frog, which secretes this psychedelic residue, and he wants to use this for essentially for helping people with addiction, and it's really powerful for that. He was over there anyway. He started telling me this story about how he had to escape Peru and took like 2 weeks, 3 weeks, and get back to civilization here. And I kind of stopped him. I was like, right, this is amazing. You're a really cool guy. You have to come on the show and tell everyone this story. So the plan is going to do that. We're going to try and do it the sort of weekend, after the weekend, next week, and do part 1. And then he's going to tell us about he's going up to Loch Lomond to do essentially like a retreat with some people who are recovering addicts, and use the Cambo for that. And then potentially at the end of this process, I may take it myself and go through the process and see what it's like and report back. I've not decided on that yet. I don't want it to be sensational or anything like that. And I'll be thinking very deeply about whether and how I want to do it and how I want to present it to everyone online. But I think we'll do that over the first couple of conversations with the dude. He's really nice. I think everyone's going to really enjoy those ones. So keep an eye out for those when they come out. And right, I think that's blah, blah, blah. I've been talking away for ages. Thank you so much, everyone. have a nice evening, and I'll leave you with I'll do the Star Wars song again. I wrote this on my loop pedal the other day with Star Wars playing in the background. So here you go. Peace out, everyone. Much love. Bye bye.
Never return from this awful place. Of course I'm funny, and you should be too. Landed Calrissian and poor Chewbacca never return from this awful place. Of course I'm funny, and you should be too. Landed Calrissian and poor Chewbacca never return from this awful place.
By your presence, you made it. You may dispense with the pleasantries, Commander. So, Commander, for your sake. By your presence. You may dispense with the pleasantries, Commander. I hope so, Commander, for your sake. By your presence. You may dispense with the pleasantries, Commander.
Christian and poor Chewbacca never returned from the...